Okay, so this is where we left off. So now we have to basically solve this. I will rewrite the equation in a more suggestive way, right? So I will rewrite in a more suggestive way. I can write it like this, right? Because you see, this is a bunch of constants. This is a constant. So I can kind of simply clean it up and put all those constants together. And you'll say, oh, that looks like a differential equation for a sine wave or a cosine wave. And then this has the meaning of a wave number. So when I globbed everything up into k, you can check for yourself that k equals 2me over h bar. And you say, well, this is just an equation for simple harmonic motion. What's the next thing that we do? We write down the general solution, right? And so the general solution is psi of x equals a sine of kx plus b cosine of kx. Check it for yourself. Just go ahead, pause the video, take two derivatives, and see that you get back the function, you get the psi back, but it will be multiplied by minus k squared. Check it. It's good for you. Check it. Okay. I can also write it like in the form a sine of kx minus phi naught, but this will be more useful form. So I'm going to stick to this form. I'm going to stick to this form. What's the next thing that we do? Okay, the next thing on the agenda is to apply the boundary conditions. Why do we do that? In order to fix these coefficients, right? Apply the boundary conditions. What are the boundary conditions? Well, the wave function, let me write it like this so you're not confused. So wave function equals 0 at x equals 0. Okay, 0 equals a sine k times 0 plus b cosine k times 0. Okay, this is 0 and this is 1. So this tells me that b must be 0. Okay. Okay. What's the other boundary condition? The second boundary condition was that the wave function equals 0 at x equals L. Okay, so now we have wave function equals a sine of kx because we knocked out the b part is gone. Okay, so at x equals L, L, we have 0 equals a sine k times L. This can happen either if a is 0, well, then we don't have any wave function, we just have a 0. It's a trivial solution. Okay, so, or KL equals n pi. Exactly like with the wave on a string. So there's a reason we did all those things, right? So either a equals 0, that's a trivial solution because it just says that all the wave functions are 0, there's no particle. Or KL equals n pi. N equals 1, 2, 3, and so on. We don't need to include negative n's. It doesn't really bias anything. Okay, so boom, we get a ladder of solutions. Okay, so we run into quantization. We get a a discrete ladder. It has discrete steps, step 1, step 2, step 3, step 4. Psi sub n of x equals a sub n sine of k sub n x, where k sub n equals n pi over L. And n equals 1, 2, 3. It can't be, n cannot be 0, because then again, if n is 0, k sub 0 is 0, so you don't have a wave function, right? Next thing, what I'm going to do is I'm going to normalize each modal wave function, okay? It's not necessary, but it will make a set of modes that we can choose from a little bit cleaner, nicer. It will already be pre-normalized. Okay, so normalize each mode, right? Okay, so so what does that mean? What does normalize each mode mean? Well, remember the full wave function for each mode is a sub n sine of k sub n x e to the minus I e sub n over h bar. We will see what e sub n is in a moment. Times t, right? Normalization means psi sub n star, psi sub n dx between 0 and L. Now, when we compute the complex conjugate and multiply by the wave function, these terms will add up to 1. And so what this gives us is this gives us a sub n squared. Well, actually not a sub n squared, because a sub n can be complex, right? So what this gives us is a sub n squared times sine squared k sub n x dx equals 0, right? Now, between 0 and L, the integral between 0 and L of sine squared k sub n x dx, where k's take on one of these values, comes out to be L over 2. You can check it for yourself. I'm not going to go into the math of that. So this tells me that 2 over L equals magnitude of a sub n squared. So the magnitude of a sub n must be square root of 2 over L. Now a sub n can be a complex number. What I'm going to do is I'm going to set all of these to 0. I'm going to make them all real. If this is giving you headache, don't be too concerned, okay? This is not like, don't relax, just relax. All I'm doing is I'm going through a normalization procedure of each mode. So long story short, I now have a set of modes that I can put on the shelf. They look like this. Okay? Nice and clean. Remember that E sub n equals h bar squared k sub n over 2m. Just from the definition of k. Remember, right here, when I clean things up, right, I put everything together in one pile, right? I multiplied by 2m divided by h bar squared, multiplied by -1. I cleaned it up and I put all of that crap into one thing, and I call that k, kind of foreseeing that I'm going to be looking for sinusoidal solutions, because those are the ones that you can pin down at the boundaries. And okay, so you get that, so you can square it and you get E sub n And now if I put this in, I get h bar squared k squared. No, sorry. H bar squared pi squared over 2ml squared. It's just a bunch of constants times n squared. So I get a ladder of energies. So here's my energy axis. And notice the first thing that you would notice, that the first state, so this is n equals 1, and it has energy 1. And the energy of the lowest mode is not a 0. Okay, I'm running out of batteries soon. Energy of the second mode is 4 times energy of the first mode. Energy of the third mode. So maybe if I wanted to represent this more faithfully, I would probably draw it like this, right? And energy of the, what's the energy of the third mode? Exactly, it's 9 times E1. How about the modes themselves? What does each mode look like? Okay, so I'm gonna depict each one of these modes. So here's my x-axis. Here's 0, here's L. Here's the first mode, okay? K sub 1 is pi over L, so when x equals L, I get sine of pi. Okay, the second mode, it looks like that. Third mode looks like that. Okay, so these are psi sub n's. I'm just sort of separating them. How about probabilities? The probability distribution. Well, remember this is psi sub n star psi sub n. The temporal factors will disappear, and this is just psi sub n star psi sub n, but my spatial part is real. So this is just psi sub n squared, psi sub n part real. Okay, so I get this. Probability density in the first mode looks like this. This is basically like sine squared of k1x. In the second mode, what happens if you square this guy right here? What you would get is you would get a node in the center. Okay, and what about the third one? You would get 2 nodes, right? You would get 2 nodes, and just sort of you would get 1, 2, 3. Really bad drawing, really bad, ugly drawing. It's very hard to draw on a, it's not easy to draw on the board, and it's even harder to draw on the iPad. All right. Okay. So this is n equals 1, 0 nodes. Well, or you could say 2 nodes at the edges, right? In the middle. N equals 2, 1 node in the middle. N equals 3, 2 nodes in the middle. So this is a probability density when a particle is either in the first mode or the second mode or the third mode. This is interesting. Let's step back. What does it say? It says that particle will never be found at those positions, right? So when it's in the first mode, it's most likely to be, when it's in the first mode, it's most likely to be found in the center. When it's in the second mode, it's most likely to be at L over quarter or 3L over quarter. But it will never be in the, it will never be at this point. The probability density goes to 0 there, right? So the probability for the particle to be within an infinitesimal a region around L over 2 would be 0, right? In other words, if you perform an ensemble of measurements, you would get a lot of measurements of position here and a lot of measurements of position here, but never here. And in the third mode, if you have an ensemble of experiments, you would get a lot of measurements of position here, a lot of measurements of position here, a lot of measurements of position here, very few sort of here, and never at these nodes, right? Probability density there is 0. Remember, P is not probability, it's probability density. So to get probability, you have to multiply it by dx or integrate over some finite region of x that gives you the probability of finding within that finite region. Okay. And by the way, the math for this is what P sub n of x equals psi squared equals 2 over L sine squared K sub n x. That's what I'm depicting here. Okay, so these psi's, the psi's, not the psi squared, but the psi's look just like standing waves on a string of length L. So we were already warmed up, right? The reason we did the string, and first to practice separation of variables, you have another practice problem on this homework with the heat equation. Here's the third example, and hopefully you're starting to see the pattern. The first mode, psi1, is called the ground state. This is called ground state. And these are all called excited states. Note that each new mode is successfully even and odd with respect to the center. This is even, this is odd. This is even, the next one is odd. Also, as you go up in energy, each state has one extra node. As you go up in energy higher and higher, each state becomes more and more curvy. It will turn out that the curvature is basically related to the energy. So the more curvy the wave function is, the more energetic is the particle, right? So the energy of the kinetic energy of the particle is basically related to the curvature. So it makes sense that you have more nodes because you're kind of squeezing more and more of these accordion wiggles, and each wiggle has higher and higher curvature. All of these features, ladder of states, increasing the number of nodes, increasing curvature, non-zero energy of the ground state, all of that will apply to more realistic scenarios. So that's the advantage of looking at very artificial models. They don't describe anything specific, or you could contrive an experiment, like have two capacitors, charge them a lot. You basically have an approximation to an infinite wall potential, but it's kind of still artificial, even though you can build it. But they're good training wheels because they contain a lot of features that are retained even in more realistic problems. So this number of nodes, number of antinodes, ladder of states, non-zero value of the ground state, and so on and so on. So this is a really good starting point in studying bound states, and we will come back to it again and again. It's amazingly educational, it's amazingly rich. Okay, so, well, this is a good start. Here's basically your equation that describes the energies. And so here it is. Here's our king, quantization, right? Quantization. The energy is quantized. It's not continuum, it's quantized. It takes on specific discrete values. That doesn't happen in classical physics. Even though the shape of the string is quantized, it's either in this shape or in this shape or in this shape, the standing wave pattern. But the energy of a string can be anything, right? With strings, you can have any energy, right? You can put the string in the first mode and crank up its amplitude so that it stores as much energy or as little energy as you want. With particles, the energy is quantized. So this is, you see, this is energy cannot be anything except these discrete specific values. That's quantum mechanics right there, right? So discretization of energies.